Hi everybody and welcome back to our data structures and algorithms series. In this video, we are going to continue our learning about binary trees and we're going to learn how to traverse a binary tree. There are many ways to traverse a binary tree. You can use something called breadth first traversal, which is also known as level order traversal. And then there are depth first traversals like inorder, preorder, and postorder. So in this video, we are going to learn about these different types of traversals, and we're also going to implement these traversals in C++ using the code that we implemented in our previous video when we implemented a binary tree. So let's get started. Now, the first traversal that we are learning is breadth first traversal, or also known as level order traversal. So the best way to do this is to walk through with an example. So let me just draw up a quick binary tree here. So in breadth first traversal, we start from top down and we visit each node from left to right or right to left. In this example, we're going to start with our root, and then at the next level, we'll go left to right. So if we look at this tree right here, our level order outprint would be 5 because we start with the root. Then we go to the next level, go left to right. So it'd be 3 and then 7, 3, 7, and then we go to our next level and it's 1, 4, 6, 9. So we looked at this and we can figure out what the level order traversal is. But how do we implement this programmatically? Well, in this case, we can implement this using a queue. So we could define a queue, and in the beginning, it would be empty. If we have a root to our tree, we add it to our queue. So I'm going to show, this is our queue, and then every step, I'm going to show you how our queue changes. So we see that we have a root in our tree. So we add that root, which would be 5. That's the node. Now our queue just has 5 in it. We look at this and we dequeue. So we remove 5 from our queue. And then if we wanted to create our outprint here, we would outprint 5. So our queue then becomes empty. But we look at our nodes, left child and right child, and add them to the queue. So we remove 5, but 5 has a child to the left. So we add 3 to our queue, and it also has a child to our right. So we add 7 to our queue. Remember, a queue works by first in, first out. The first element in our queue is the first to be removed. So we remove 5, but we add 3, and then we add 7. So now we go through our queue, and we see that 3, we remove 3, we can outprint it here. And then we look at 3 and we see that it has 1 and 4 as its children. So our queue becomes 7 being in the front, and then 1 is queued because it's the left child and left goes first, and then 4 is queued. So now we reach 7, dequeue 7, can outprint 7. We look at 7s, it has 6 and 9, so this becomes 1, 4, 6, 9. And then we can look at 1. 1 ends up having no children, so we don't add anything to the queue. So we dequeue 1, outprint 1. Same idea with 4, dequeue 4, outprint 4. Same idea, right? No children. Dequeue 6. 6 has no children, nothing to add on. Outprint 6. Dequeue 9. 9 has no children, nothing to add on. And we're outprinting 9. Now our queue is empty. And when our queue is empty, we don't need to go any further. This is how we are going to implement our level order search programmatically. We're going to use a queue, which we have learned about in our previous videos. we're going to use C++'s standard template libraries queue. So when I say enqueue, that's going to be push. And when I say dequeue, we are going to pop. So now let's write this programmatically. So what I have here is the binary tree implementation we did in the previous video. I've included our standard template library for a queue because we're going to use that. And I've already defined our public function print level order. So now what we got to do is implement it. The first thing that we have to consider is that our binary tree could be empty. The way that we can tell that our binary tree is empty is that our root is null. So if our root is null, we're just going to get out of this by writing tree is empty. Now we can implement the remainder of what we just walked through. So otherwise, let's write this code. So first we need to define our queue. So we are going to have a queue that holds the type node because we will be adding nodes to our queue. And then we look at the left and right. So the first element we add to our queue is the root. So queue dot push the root. In the standard template library, push means the same thing as enqueue. Now, we've defined our queue. We added the root to our queue, so we added 5. Now we need to look at our queue and loop through it until our queue becomes empty. So while our queue is not empty, then we want to dequeue the first element in our queue, outprint that value, and then add the left and right children if they exist. First, we got to get the first element in our queue's value. In order to do that, we have to look at the front element in our queue and save it into a temporary variable. So we can say node and it's queue.front. This is similar to peak. Then we remove the node from our queue. So we can say pop. This pop in standard template library is the same as dequeue. And we want to outprint our node's value, right? So if this was 5, we've stored it into a temporary value. Then we removed 5 from our queue, and we're going to print 5 to our terminal. We say cout n value. So we've removed 5 from our queue, and we've outprinted 5 to our terminal. We then need to add 3 and 7 to our queue. So we have to add the left child and the right child if they exist. So if n left does not equal null, we want to push the left. And similarly for the right, if n right does not equal null, queue.push n right. So this will loop through that entire process we did and outprint it and outprint our level order traversal. The last thing we want to do is basically we printed this all out. It's all in the same line. We want to do a line break. So we're just going to do cout end line. This is how we implement the level order traversal. Let's test our code. So what I have here is the binary tree that we've done in this example. So this is just inserting all the values for our binary tree. And if we run this, we should see the outprint 5, 3, 7, 1, 4, 6, 9. And actually, for good measure, let's test also our empty tree and let's print our level order while our binary tree is empty. So our outprint will actually be tree is empty and then 5, 3, 7, 1, 4, 6, 9. And there you have it. First outprint is tree is empty, and then our level order traversal 5, 3, 7, 1, 4, 6, 9. Now you know how to implement level order traversal. Let's now learn about our depth first traversals. So there are 3 types of depth first traversals: inorder, preorder, and postorder. And we're going to learn about each types of the traversals, and then we will implement them in the code that we've been doing so far. Let's walk through in order. In a binary tree, like a binary search tree that we have as an example here, in order is kind of what you would expect. The outprint is going to be in order. What that means is we outprint first the left, then we outprint the root, and then we outprint the right. So if we start at the root 5, we go to the leftmost node. So we go down to 3, there's still one more left. Go to 1. So this is our leftmost node. So we start at the left, then we outprint 1. So we'd end up going 1. Then we end up at the root, which would be 3. Then we outprint the right, which is 4. We've already visited 3, so we do not output 3 again, but we would outprint 5 because that's the root, because this is actually the left of our root's 5, right? So we'd outprint 5. Then we go to the right. Right is a root. There is another leftmost. So we end up at the right, but there's a leftmost node. So we outprint 6. Then we outprint our root, which is 7. And then we outprint the right, which is 9. So the result for our in order is 1, 3, 4, 5, 6, 7, 9, which is actually our binary tree sorted. In preorder, our root is visited first, and then the left subtree is visited, and then the right subtree is visited. So it works in the order of root, left, and then right. So in the case of preorder, we start at our root, which is 5, and we would outprint 5. Then we move to the left, which is 3. 3 is the root of another subtree, so we visit 3, we outprint 3, and then we go to the left, and we end up at 1. So we outprint 1. Then 1 has no children. It's not the root. It has no children. So we go back up to our root, which is 3, and then go to the right, which would be 4. 4 has no children. So we go back up to the root. There's nowhere else to visit. Go up to 5. We've already visited 5's left subtree. So we go to the right, and we visit 7. Then 7 is the root. We have a left child, which is 6. So we visit 6, outprint 6. This has been visited. It has no children. So we go back up to the root and then visit our right, which is 9. So in the case of preorder, for the tree that we have as an example here, it would be 5, 3, 1, 4, 7, 6, 9. Now, postorder. Postorder traversal is where we visit the leftmost node, and then we visit the right, and then finally the root. So it works as left, right, root. In the case of postorder, in this example here, we visit the leftmost first. So we start at our root, go to the left, that's 3. It has a child to the left, which is 1. 1 goes back up to its root. The root has a right child, so we outprint 4. Then go back to the root, we visited both children, so we output 3. We output 3. Then we go back up to 5. So 5 is the root. We've already visited this left subtree. Now we need to visit the right subtree. So we do not outprint 5 yet. We go to 7. 7 has a left child, which is 6. So we outprint 6. Then we go back up to 7. It has a right child, which is 9. Then we outprint the root, of this subtree, which would be 7. And then finally, we outprint the root of our overall tree, which is 5. So now you've learned how to walk through inorder, preorder, and postorder for a binary tree. We're looking at the overall binary tree, but we also investigate the subtrees in that binary tree. And that's how we determine our inorder and preorder and postorder. So similarly to our previous video, where we implemented our inserts and searches and deletes, we need to do recursive functions because a binary tree in itself is recursive. Let's implement each of these depth-first traversals using recursion. The reason that we went over all these beforehand is actually the implementation of inorder, preorder, and postorder are very similar. What's going to be different is when we choose to outprint. So let's implement these. So what I've done here is I've already defined the functions that we need to implement. We need to implement our inorder, preorder, and postorder methods. And to get into these methods, we're going to have a public method, and those would be called print inorder, print preorder, and print postorder. If we recall, when we walked through our inorder, preorder, and postorder examples, we always started with the root of our tree. Because the root of our binary tree is private, we also have private methods that are going to be passing in the root. And as I mentioned earlier, our binary tree is a recursive definition. We have subtrees as well within our binary tree, and those each have their own root. So we have 5, we also have 3 with its own binary tree. So just like in our previous video, our parameter is going to be a node, and that node will be called leaf. So let's first implement inorder. Our initial public method for our preorder call is going to actually just call the private method, passing in the root, which is the starting point for all of our depth-first traversals. So once we go into our inorder function, we start at the root of our tree. Now, remember, in our inorder implementation, we first visit the leftmost node, and then we go to the root of that subtree. So if we start at 5, we first need to traverse down to our leftmost node, which is 1. So, assuming that our tree is not empty, we need to outprint the leftmost node. So we can say if our leaf does not equal null, then our binary tree is not empty. We'll assume we are at 5. If we end up at 5, our leaf is not null, so it's the root of our tree, we need to continue going to the left. So we would call our recursive function, so we're going to call print inorder, and move to the left of our leaf. So leaf left. So we do this, we're starting off at our root, we go to the left. So we end up going to 3. If we look at 3, our leaf is not null, so we go to the left, which is 1. So we end up at 1, it's not null, so we go to the left, which is null. So we call print inorder null. So we end up here, the leaf is null, we break out of our recursive function. Then end up popping back up to this call here. So we need to outprint 1. So we call cout leaf value. This outprints 1. Now we've end up at 1, we outprint 1, we go to 3, we're going to end up outprinting 3. However, at this point, we have the right that we need to traverse to. So we need to make sure that even though we're at 1, we also need to look and see if there's a rightmost value. We call print inorder leaf right. So if we walk through this function again, we start at the root of our node, which is 5. We move to the left, which is 3. We move to the left again, which is 1. We move to the left, it's null. We break out of our loop, we outprint 1. Now we look and see if 1 has a child to the right. So we print inorder right. Well, that's null. So we break out of the loop and we end up going back to 3. So we outprint now 3. And now we check if 3 has a child to the right. Call that's 4. So we end up at 4. We print the left, which is null. So there's nothing to print out. We break it. Then print 4. We call print in order right. There's nothing to the right, so it's null. So we break out. We're at 4. So we're here now. That's 3's call. We break out of the stack. We end up going back to 5. Now we print out 5. And then, similarly, we end up doing the right subtree. So, recursion might be a little hard to envision, but again, walking through these steps and making sure that you are lining up correctly will lead to the correct implementation. Now, with doing this implementation with inorder, we can easily write the preorder and postorder implementations. But don't worry, we're still going to walk through them just in case maybe this was a little confusing. Going through it 2 more times might help. Now let's implement preorder. Preorder, we start with the root. So we outprint the root first, and then we print the left and then the right. Our public method for preorder, we don't know the root yet, so we want to call print preorder, and we pass in the root. If our leaf is not null, which means that if our tree is not empty, we need to do our recursive method. In preorder, we print the root first, then we visit the left, and then we visit the right. So we first outprint our root. So cout leaf value. So this outprints our root first. Then we want to go to the right. So we call print preorder leaf left. So at this point, we've walked down, we visited 5, we outprinted 5, we went to 3, we outprint 3. We now go to 1, we outprint 1. We go to 1's left child, which is null. Break out of that recursion, we pop up the stack to 1, and we need to visit 1's right, which still is null. But we have to visit it, right? To find out that it's null. So we say print preorder leaf right. So 1's right is null. So that breaks out this 1. We pop up to 3 stack. 3 now then ends up going to the right, which outprints 4. And continue on this path. So this is how we write the preorder traversal. Now there's one thing that I'm going to do just for cleanup for our outprinting in our terminal. As we're printing all these on the same line, I just want to make sure that when I call inorder and preorder that the line is going to break. So I'm going to add a line break between these here. So cout and line. And the same here. You've seen how we implemented inorder, and you saw how we implemented preorder. Probably got an idea of how we're going to implement postorder. So first, we always start with the root of our tree. So let's call print postorder root. And then we will have our line break as well. So if our tree is not empty, we got to keep traversing our tree. So if our leaf does not equal null, you're going to visit our leftmost subtree first. We call print postorder leaf left. So we're starting at 5. 5 is not null. We go to 3. 3 is not null. We go to 1. 1 goes to the left, which is null. So it breaks out. It goes back to 1. So then we would want to outprint 1. So we say cout leaf value. Now remember, we want to outprint our rights value before we outprint the root. We're at 1 because the child to the left is null. But now we have to make sure we also visit the child to the right before we outprint the root. So we call print postorder leaf right. And we're calling this beforehand. So we traverse to the left, then we traverse to the right before finally outprinting that leaf. So we walk through this code here. end up at 5, which goes to 3, which is going to call the left. This goes to 1, which calls the left, which is null. That's our break. So we break out of the recursion, end up back at 1. We call its right, which is null. So we break out of the recursion, go back to 1, and we outprint 1. That breaks us out of the recursion. We end up at 3. 3 has only called the left at this point. So now it calls the right. 4's left and right are null. So it ends up calling both these. It ends up being null. So it outprints 4. Then it ends up at 3. 3 has completed these recursive functions. So it outprints 3. So that's how we get 1, 4, 3. We end up at 5. 5 has done all its left calls. But now at this point, it needs to do its own right call. So it ends up calling 7. And then 7 does its own left and right calls. So we've written our inorder, our preorder, and our postorder traversals. Let's now test our code. So go down to our main method here that we have as our test, and let's call each one of these. And there you have it. Our inorder is 1, 3, 4, 5, 6, 7, 9. That's in order, it's sorted. Our preorder, as we walk through here, is 5, 3, 1, 4, 7, 6, 9. And our postorder, as we walk through, is 1, 4, 3, 6, 9, 7, 5. So now you've learned how to implement the depth first traversals, in order, preorder, and postorder. You've also learned how to implement our breadth first traversals. So you went through all this, you learned how to implement these things, and aside from the fact that this is something you have to learn in data structures and algorithms, and it's a interview question that for some reason Google really loves to ask, why does this matter? Well, trees are used for hierarchical structures. So each node contains certain information, and to get that information, we have to visit each node. And with that, we have to, 1, know these different types of traversing algorithms. We learn these traversing algorithms because they also can answer certain questions. For example, we might want to know the size of our tree, or we want to know the maximum value in our tree. So if we're doing in order, we want to know the largest value in our tree. We could also want to know the smallest value in our tree. So in order to know that, though, we have to traverse the whole tree. So doing something like in order makes sense because we can find that minimum and maximum easily. A tree data structure is also used to represent those hierarchical relationships that I mentioned earlier. HTML and XML are examples of markup languages that actually use tree structures. So in those cases, the root has child branches, and then inside, so like the root would have the child branches, and then inside those, they can have their own subtree with their own branches. That's something that HTML and XML do. Another thing is that when you're looking at file paths on a computer, you have a root directory, and then you have child branches, which are all your subdirectories, and they may have their own children, which again are subdirectories. So when you're trying to look for a specific file, doing different types of traversals is the types of algorithms that you would use in order to find that file. So, as abstract as it seems here, these do relate to real-world examples where you would use these types of traversals. So it's not just an interview question. It is also an important structure that is used in solving many problems in software engineering. So if I'm saying that they're used for solving different problems in software engineering, then that comes the question of our space-time requirements. So when would you use a breadth first search versus a depth first search? That comes in terms of the space that we have. So when we start thinking about our tree traversals in space, there is a difference in terms of the extra space required. The extra space required in our level order traversals is OW. And W is the maximum width of a binary tree. This is because, as we learned in our level order traversals, a queue stores our nodes one by one, and they're from on a different level. When we do a depth first traversal, the extra space that is required is OH, and H is the maximum height of our binary tree. That's because in our depth first search, a stack, or in the case of the fact that we've done a recursive function, it's a function stack, stores all the ancestors of a node. So now we have to start thinking about what is our maximum width, or that worst case, when we do a level order. The maximum width of a binary tree at its depth or height can be 2h, where h starts from 0. So if we're talking about this, the maximum number of nodes can be at the last level. If we're thinking a binary tree and it keeps expanding, the maximum amount of nodes can be at the last level. And the worst case is when our binary tree is a perfect binary tree. So in the worst case, the value of 2h would be the CEL of n over 2. So we're talking O n. So now we're thinking, okay, that's the worst case when we're talking about the level order traversal. We're looking at O n. So let's talk about now the height of a balanced binary tree. So the balanced binary tree, as we learned earlier, can be log n. But the worst case for the height of our tree can be a skewed tree, where our tree is really just essentially a linked list. In that case, the worst case of our depth first traversals is O n. So if we're looking at this, when our trees are more balanced, it's better for us to use a depth first traversal algorithm. If our trees are more skewed, it's better for us to use the level order traversals. But it gets really complicated because you don't really know all those things. So you might ask yourself, which tree traversal should we choose? Well, extra space can be a big factor when you're choosing tree traversals. Depth first traversals are typically recursive, and recursive calls require function call overhead. But the most important point that we keep here is that we're looking at this because we're searching for something within the entirety of our tree. We are looking for a specific file in a hierarchy of folders. And if we remember this, our breadth first search or our level order traversals start from the root, whereas our depth first searches are visiting nodes at their leaves. So if our problem that we are looking to implement is searching for something that's more likely to occur closer to the root, then we should choose a breadth first search. We should choose the level order traversal. If, however, the problem is more likely to be closer to the leaves of our tree, then we would prefer a depth first search or a depth first traversal. This comes back to the major fun of software engineering in general and being a computer scientist. We have to analyze our problems. We have to do a little bit of research, and then we see what is the best implementation to do based off of the factors that we know. So we have to understand our problem and then create the solution. Now that you understand all these different types of traversals, then you can say with more confidence that in this scenario we should use inorder, or in this scenario we should actually do a level order traversal. It all depends on the problem you are trying to solve. Congratulations, you have learned about different types of tree traversals. You've learned about level order or breadth first traversals. You've learned depth first traversals, inorder, preorder, and postorder. And you've learned how to implement all these types of traversal. In our next video, we are going to learn about how to balance a binary tree. So if you liked what you saw, please remember to subscribe to my channel so you can be notified for the next video in this series and any other videos you may be interested in. Until then, happy learning!